Okay. So today, so let's start the class. So before we start the class, I want to just tell you, I posted a small homework in the classroom. I mean, it's pretty straightforward, this thing. It's mainly about the specification. I hope you had the chance to look at it. I mean, I just gave a week because from now on, this theory homework at least we should be able to do it fast. Yeah, this is the theory thing. It's a few questions. I mean, it's about the location of Praj, SSB, and other things, SIB1 message and TD structure. It shouldn't take too much time. Please, I suggest everyone to finish this fast so that I can give the next homework and we can. It is a theory part of the things we can do it fast. Okay. Okay. So with that, let's start today's class. So in the previous classes, we have learned. We were looking at videos on LDPC encoders and LDPC decoders. At least we understood what is meant by cryptograph, what is meant by expansion factors, and how is the code specified. Okay. So those of you interested, I encourage you to finish up those videos. There are a few more videos which talk about the LDPC decoder and similarly on the polar side also. I'm not going to focus on the polar because we will not have time. Andrew also actually does a lot of there's good lectures on polar encoders and decoders by Professor Andrew. Okay, the same series. Okay, so those of you interested, I strongly encourage you to finish up those lectures. They're very nice. I mean, it gives you a good grasp of things. So, saying that today we will start about the transport channels and HART. We'll start with the transport channels for today, and we will understand how bits are processed. I mean, what is the framing structure there, and how is it mapped to constellation points? Okay, those are the things that we are going to do now. Okay. So, any questions in the previous classes before we start? I can just spend a couple of minutes. We can address a few questions and then move forward. Good. Okay. So now what did we finish till now? Till now we finished both the synchronization channels. We finished the PBCH, the broadcast channel PBCH and the SS block, as well as the Pratt channel. Okay, we also did a little bit about TD structures and other things, but from a channels perspective, we finished PBCH as well as Pratt. Okay, now it's time for data. Okay, so where does the data come from? The data comes from the higher layer, the MAC layer. Okay, they come in terms of the transport channels. In this, the transport channel is called the downlink shade channel. That is mapped to the physical channel called the PDSCH. Okay, downlink shade, physical downlink shade channel is called PDSCH. Okay, so we are going to focus on the PD. We are going to focus on PDSCH now, and see what is the processing that happens in PDSCH. Okay. So just to recall, PDSCH is the main data channel, okay, in the downlink. So and all the data, actual data is sent to the PDSCH channel. Okay. There's also a control channel called PDCCH. We'll look at that after we finish this. Okay. So the interface between the MAC layer and the L1 layer is called the transport block. Okay. So MAC layer sends transport blocks to the physical layer or the L1 layer. Okay, and the L1 layer processes this transport blocks. Okay, so these transport blocks are UV based. So each UV will have it UV. I mean, so if at that time instant the base station is serving 3 UVs, each UV will have its own transport block that the base station transmits. Okay, and up to 2 transport blocks per TTI. Per TTI means essentially per 0.5 milliseconds in a slot. Okay, TTI is transport time interval. You can think of that as a slot here, 0.5 milliseconds in 5G NR for 30 kilohertz. Okay, when I'm talking, it's 30 kilohertz. Okay, so their maximum of 2 transport blocks are allowed. Okay, again, the size of the transport block is very dynamic. That's what we're going to look at, and how it is rate matched and other things. Okay, so what happens is if you have less than 4 layers, only 1 transport block is allowed. If you have more than 4 layers, 2 transport blocks have to be used. Okay, that is the deal. That is the spec. That's what the spec says as the interface between the MAC layer and the physical layer. Okay. Any question? Okay. So remember, the transport block is always UV oriented. Each transport block goes to one particular UV. Okay, so you have 10 UVs you are serving, you have 10 transport blocks that are coming from the MAC layer to the L1 layer. Okay, everyone is using less than 4 layers. If some of them are using more than 4 layers, then 2 transport blocks per UV will come. Fine. Okay. So this is a very, very high level block diagram of the transmitter. Okay. So we have the MAC PDU, which is a transport block that is sent to the physical layer. This is the physical layer. The physical layer, the first thing that happens is something called the transport block CRC. CRC is added to that. Okay, we'll come to the details of this. Then what happens is things are segmented. The transport block, after you add the CRC, they're broken into small pieces. Again, CRC is added. And for each of this small broken thing, you do LDPC. Then you do rate matching. And then whatever you have broken, you again combine them back. Then you do something called scrambling. The reason why they do scrambling is to make sure that there are enough, you don't have a constant stream of ones or constant stream of zeros. Okay, so you do scrambling, followed by modulation. Modulation, all of you understand. Okay, you do QPSK 16 gram to 56 gram, followed by layer mapping. So layer mapping means essentially you are mapping these modulated symbols to different antennas. Pre-coding, RE mapping, then IFFT and antenna. This part we know already. We have seen the IFFT and other things. Okay, so in this set of lectures, we're going to focus from this point all the way up to modulation, up to layer mapping. Okay. Then I'll talk about MIMO, and then I'll teach you about the pre-coding part of it. Okay. So for now, we'll focus from here, this block to almost this block, to the layer mapping. Is this fine? Any questions?
So the segmentation, concatenation, both are happening on the transmitter side only, right?
On the transmitter side. I'm just talking about the transmitter side.
But why then segmentation was required if it is done at the same?
Yeah, it will become clear. Just by the end of this class, it will become clear why we require that. It has to do with the LDPC. Okay. So now let's start from the beginning. We'll look at the MAC PDU. So this is going to be a little bit. I'm going to go through the details of this. What are the sizes of the PDUs that are allowed? Why is it broken? All these questions we'll answer. Okay. The first thing is the transport block. Okay. So these are MAC packet units. Okay, packet data units, and they come from the MAC layer. So as I said, transport block is per UV. Every transport block goes to 1 UV. Remember this. Okay. So transport blocks go to each transport box goes to 1 UV. So for 4 layers, if you have 4 layers, up to 4 layers, you can have 1 transport block. After 4 layers, you will have to have 2 transport blocks. Right? This is the only thing that you have to remember as of now. What is the size of a transport block? This is a very big question. We'll answer this at the end of this whole thing. You will start getting a flavor of how is the size of the transport block determined. We will get to understand. Okay. So, sorry, just 1 minute, let me collect my iPad. Got this right. So let us first understand what are the different issues, and then we'll proceed. Okay. So you have a resource grid. Finally, the resource grid is what is transmitted. Okay. So resource grid, this is time. This is frequency. Okay. Okay. So each user is allocated some parts of the resource grid. Okay. For example, a user 1 might be allocated these parts of the resource grids. Okay. A user is allocated these many parts of the resource grid. So for example, if the number of resource elements in this allocation, the user allocation is some X, not X, maybe maybe I'll put beta. Okay, so beta resource elements are allocated. Okay, so beta resource elements are allocated, and Suppose you use 4 QAM for all the things. Then how many bits he can put maximum? If the user uses only 4 QAM for that resource elements, then how many bits he can, how many bits he can fit in this grid? Hello.
Yes, sir.
You understand my question? No? There are the total number of resource elements are all beta.
Beta, yes, sir.
And each can be filled by QPSK symbol. So
Yes,
how
sir.
many bits per QPSK symbol? 2 bits.
Two
So the
bits,
total
sir.
he can put is 2 beta. 2 beta, correct. Yeah. Suppose instead of that, if he uses 16 QAM, he'll be able to fit 4 beta, 64 QAM 6 beta, and so on. 256 QAM 8 beta. Okay, that's one question, one issue. So the number of bits he can fill in the resource grid depends on the modulation. Okay, the modulation index is QM, the modulation index that he has. Okay, that's one issue. The second issue is that all the resource elements are not allowed to be filled with data. There will be some pilots. There will be some pilots. I mean, for example, this may be a pilot. 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 Okay. So what we should do? So in the total, from the total number of resource elements, you subtract off number of pilots. Okay, number of pilots that are used. Okay, and then this into log 2 of the modulation that he's using will be the number of allowed bits. Yes.
Yes, sir.
Okay. So now the problem is LDPC code. Okay. So what happens? So this number may be very weird number. It may be very, I mean, it can be any number technically, depending upon the number of resource elements you allocate and other things. Okay. So things, actual resource, I mean, they generally allocate resource blocks. I'm just calling resource elements so it's easier. But generally, all the allocations are done in terms of resource blocks. Okay, just remember that. Okay, so now the question is the output of LDPC, whatever you have encoded, after you do the modulation, should fit in exactly in the grid. Okay, so that's a little bit difficult. How do you make sure that it fits exactly in the grid? Okay, so this is where this rate matching, why this code block segmentation has to happen, all those things come into picture. Okay, so what we are going to see what is going to happen is LDP, there's going to be only 2 fixed LDPC codes. That's what Andrew said. No? There are 2 base graphs. One is base graph 1 and one is base graph 2. Okay, and they have some fixed rates. So the outputs and the input relations are kind of fixed for LDPC. The number that goes into it and the number that comes out of it are fixed. Okay, but this grid size is vary. Depends on your allocation, depends on the user need, depends on the allocation. So this whole grid size varies. Okay, so how do you make sure things fit in exactly without any problem? Okay, that is one thing that we are going to learn in this class, how that happens. Okay, so this is where this whole notion of rate matching, okay, puncturing come into picture. Okay, so we are going to look at this carefully now, and once we finish this, we'll start understanding this in a much more better manner. Okay, so did you understand the high level issues that are there? Effectively, you should fill the number of bits that come out of your code should fit in exactly in your resource grid after you map to the modulation. Okay, any other questions?
So this resource grid will come into picture only on the radio interface now, right?
Yes, on the radio interface. Yes.
On the radio interface. So in the block diagram that you are telling that after LDPC it has to fit. So yeah, it has to fit only before transmission, right?
Before transmission.
Transmission.
So bits are coming from the MAC, sir. Okay, yes, MAC is sending you bits. Okay. These bits, what you do, you'll do your FEC and the things, and then you modulate into symbols.
Okay, sir. Okay, sir. So whatever the resource block is assigned, that bit has to be fit into that, right?
Into the grid. Exactly. And roughly it should be the code rate that you want. Okay, the code rate will be determined by channel conditions and other things. Huh? You want half rate with QPSK. You should make sure that things fit in. Okay, how do we do that? Okay, so this is the transport blocks. So the first thing that happens after the transport blocks is you add CRC to the transport blocks. Okay, why do you add CRC to the transport blocks? Can anyone tell me?
Repeat question, sir. Why do you?
Why do you add CRC to the transport block? So transport block came.
For
Yeah, now you are adding
channel
CRC.
error,
Why are
channel
you adding
error,
CRC?
error controlling.
So this is mainly for error detection.
Yes.
Okay. So the reason is you are transmitting something to the UV. Okay, you can think of this in the uplink also, but I will just focus on the downlink. You are transmitting something to the UV. The UV did some processing and got some bits. You should know whether the bits are correct or not. Yes. The way it will know those bits are correct or not at the physical layer level is this using CRC. It will compute the CRC. The CRC check passes, then it says this transport block is correct. And then it passes through its own MAC layer. The UV passes through its own MAC layer. Okay. The MAC may have its own CRCs. Some of the CRCs are the higher layers. Okay. So this is the first at the physical layer. The transport block CRC is very important because it will tell if the transport block is correct or not. Right? There are multiple CRC polynomials that are what do you say? So by the way, CRC means cyclic redundancy check. The multiple CRC polynomials that are there in 5G standard. There are two things that happen here. So A is the size of your transport block. If your transport block is greater than 3824 bits, you use a 24-bit CRC. Otherwise, you use a 16-bit CRC. Okay. So CRC is generally defined in terms of a polynomial. Polynomial means essentially you can think of this as a big bit string of bits. So how do you find, given a bit string, given a large string of bits, how do you find the CRC with respect to this particular polynomial? What you do is, you divide one polynomial by the other polynomial, the actual message polynomial by this polynomial, and take the remainder and append the remainder. Okay. So I will give a simple example of CRC in your homework. You can try this out. This is just for fun. Okay. So, but effectively, what you should remember is the only thing I want you to take from this slide is CRC is added to make sure that you can detect errors, and the CRC size depends on the transport block size, the TB size. Okay, if it is greater than 3824, you use 24-bit CRC, otherwise you use a 16-bit CRC. Okay, so at the output of this block, if the input block length is A, transport block size is A, the output of this block would be A plus L, where L is either 24 or 16 depending upon the size of your CRC. Is that fine? Any questions?
This resource block and this transport block, if I compare, transport block is actually the total block that is being transmitted, right?
Yeah, transport block is the total transport block that's transmitted, yes.
So it means that one UV can have only one transport block at a time.
If it is less than 4 layers, it can have one transport block. If it's greater than 4 layers, it will have 2 transport blocks, at most 2 transport blocks.
So what does it mean? More than 4 layers, which 2 transport block?
So so they'll have 2 transport blocks. I mean, see, transport block is just a set of bits.
Yes.
It's a logical unit.
So it is transmitting at a time, so only one set of bits will be transmitted, right? Yes.
So the resource grid will be larger because it has more layers. You have to fill the different layers. They are parallel layers. So they'll parallelly be filled. At the same time, they'll be filled.
Actually, with the help of a spatial multiplexing, we are increasing the data rates, so more transport block is required for that.
Okay, so layer means your MIMO. So if
layers means MIMO, sir. Layers means MIMO.
Okay.
You can transmit more data for the same, say on the same time. That's why you can use 2 transport blocks. Okay.
In future, we can have more than 2 transport block also.
No, sir. They generally no. I mean, see, the transport blocks are very fundamental. So what even LTE this was the same, because the whole process, the whole chain depends on the number of transport blocks. It's very complicated to change this.
But 2 transport blocks we are using for if layers are more. Suppose in future the size of MIMO is more than what is today. In that situation, to have with HARQ, we can have more transport blocks. What I think. Not getting a speech.
So you are not audible, sir. Professor.
Now it's coming.
Hello.
Yes, now you are audible.
Okay. It seems to suddenly stopped. Okay, so what I was saying was, in future, I mean, changing the number of transfer blocks per UV is a little bit more complicated. Technically, it can be done, but spec has to be changed. That's what I'm trying to say.
My submission is only technical.
Yeah. Technically,
But,
Technically, yes. Technically,
yes.
there is no issue.
Correct.
Yeah. Okay. Okay. So the next step that happens after the transport block CRC happens is the code block selection, the base graph selection. Okay. So like Professor Andrew was saying, there are two base graphs in LDPC. One is called the BG1 base graph 1 and the other is called the base graph 2. Okay. So base graph 1 generally can take larger number of input bits, whereas base graph 2 can take smaller number of input bits. Okay. So that's what I was saying. So LDPC encoder can support two input sizes. One is base graph 1, which can take an input size of block size is 8448 bits. And the other is base graph 2, which can take an input of 3840 bits. Okay. So how you choose your base graph is a little bit complicated. So what they do is, at this point, the scheduler will also tell you what should be the rate of your code. Okay. So before how is the MAC TB change? MAC TB made means when MAC itself does the scheduling. Okay. So when MAC does the scheduling, it also knows how many resource elements are allocated to you, what should be your code rate, what should be your modulation. Okay. So it would have determined your code rate. R is your code rate. Okay. All of you understand what is the code rate, na? So code rate. So what it says is, if your A is less than 292, or if your A is less than 3824, and R is less than 0.67, I mean, there's some condition, BG2 is used, otherwise BG1 is used. Okay, I just drew this pictorially, where on the x-axis is the A, which is, on the x-axis is the A, which is what, which is the, just 1 minute, which is the size of the transport block without CRC, and R is the code rate. So depending upon that, you choose either BG1 or BG2. Okay, there are two base graphs. That's what. Okay, so at this point, you'll also do the selection of the base graph. Okay, so at this point, you will also know which base graph you are choosing. Okay, how will this help? I'll tell you in the next minute.
Just a simple question. The CRC is scrambled by the RNTI. This CRC is scrambled by RNTI for the different. I think like
not for this. Not for this. Not for this.
Not okay.
Not for this. Okay. Okay. So one thing you should remember is the maximum number of bits, input bits, that each LDPC encoder can take is base graph 1 can take 8448 and base graph 2 can take only 3840. Okay. So what happens if your transport block is larger than this? So that is the reason why you break the transport block into something called the code blocks. Okay. The code blocks are the ones which are inputted to the LDPC. Okay. So what might happen? Your transport block might be large, very large. Okay. So what you do is you break your transport block into smaller parts so that they can be passed as inputs to your LDPC encoder. Okay. Remember, for LDPC encoder, the maximum bits supported are 8448 for basic BG1 and 3840 for BG2. Okay. So what they do is, if the input TB is larger than the maximum code block size, okay. So after you add the input, so when I say input TB, I mean input TB plus CRC. Okay. At this point, the TB CRC is done. They will break this transport block into smaller parts called code blocks and add separate CRC. They compute the CRC for these code blocks and add to them. Is this fine?
Yes. Yes.
Why do you add CRC to the code blocks? Okay. So why do they add CRC to the code blocks? I mean, finally the UV can just put together all the code blocks and find a CRC, and if the CRC fails for the transport block, it's failed. Why do they add CRC to the code blocks?
For every code block, integrity of every code block, I think for error
detection only.
error detection.
So that's partly correct. So the idea that is there is, see, if you so what happens? You're transmitting something based on that CRC at the receiver at the UV. Suppose the UV just calculates the transport block CRC. Suppose it failed. Then the UV will send back a negative acknowledgement saying that, hi, this transport block failed.
All code blocks will fail then.
Yeah. Then the base station has to transmit the entire transport block.
Yes.
Okay. So instead of that, now what happens is, if each code block has a CRC, the UV can inform the base station that, oh, my fourth code block failed. So the next time the base station will only transmit the fourth code block. It will not worry about the entire code block.
Yes. That is it.
Okay. So we are going to do this in depth when we do HART. It doesn't do that only for one code block, but we'll do it in depth for HART. But this is the main idea of having CRC, individual CRC for the code blocks. Okay.
Sir, can the code block have various size? Means their size may not be the same.
So if your code block, see, it depends on the transport block size. I mean, the code blocks generally have, all of them have similar sizes. Okay, the code blocks have similar sizes. It will become clear. I mean, let's just wait for a couple of slides. I'll tell you how this code block sizes and other things are determined. Okay. So the code blocks, even before the code blocks go into the FEC, something else happens. That's what I want to emphasize. Okay. So how do we determine the number of code blocks? This is the technique. Okay. KCB is the maximum code block size. As I said, for BG1 it is 8448 and BG2 it is 3840. Okay. So B is determined. B is equal to A plus TBCRC. TBCRC is either 24 bits or 6 bits. So now you have B bits, capital B bits. Okay. If this B is less than the code block size, the maximum code block size, then the number of, there's no need of code block segmentation. And the number of code blocks will be equal to 1. Okay, then you don't add any CRC. Okay, this B dash will become clear in a little while. We'll understand this. Okay. On the other hand, if you B, the total number of bits after you add the TBCRC is larger than KCRC. What do? This is a 24. This CRC is also a 24-bit polynomial. It's a 24-bit CRC is added for the code blocks. What you do? The number of code blocks will be equal to B divided by KCB minus L. Okay, why KCB minus L? Because you are all, I mean, whatever in the code block, you're also adding to the 24 bits now. So that's why they subtract of L. 8448 minus 24, that is 8424. You divide B by 8424, for example, if you are using BG1, and take the ceiling of it. So those many code blocks will be there. Fine. So they're actually equally dividing that between all the code blocks. Is that fine? Okay. And then they said the B dash is the total number of bits that will be equal to B, original bits, plus the number of code blocks into 24, because you're adding 24 bits to each code block. Fine. I'm going to just explain this. This is something that you should sit down and once look at it, then you'll understand this better.
Yes.
Okay. So now comes the tricky part. Okay. So now we have segmented into code blocks. Okay. Now we have segmented into code blocks. And what did we do? We added the CRC. So now the question is, now we have to choose the expansion factor for the, what do you say, for the, this one, for the LDPC code. How do we choose that? Okay. Okay. So what we say is, we say let KR be the number of bits in each code block. Okay. Keep that in the side. So there's a lot of conditions here. Okay, it says for LDPC based graph one, you choose something called KB. KB is equal to 22. For LDPC base graph 2, depending upon the size of your B was A plus TB size or CRC size. If B is greater than 640, you choose KB10. B is greater than 560, KB9 or whatever, blah, 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 blah. Okay, so you choose this KB. Okay. Then what you do is, you choose something called Z. Z is the lifting size. Okay. Z is the lifting size, and you choose KB into Z should be greater than K dash. Remember, what was K dash? K dash is nothing but the total number of bits by the code block, number of code blocks. Okay. So, I mean, I'll just show you a picture. This will become very, very clear. Okay. And then what you do is, you choose the size of your input block as 22Z for BG1. Once you choose a Z, and for BG2, you choose as 10Z. And you choose the same size for all the code words. Fine. Let me explain you this with this picture. Okay. So I'm assuming C is greater than 1. The number of code blocks is 1. Okay. So what happens is, first you have a transport block. Then you add a 24-bit CRC or 16-bit CRC depending upon that. Okay. Then this transport block is broken into some number of bits, code block 1, code block 2, which is indicated by this blue color. Fine. Okay. So the final size KR, so 22Z is the number of input bits that your LDPC encoder expects, okay, depending on your factor Z. That is called KR or K. KR is equal to K. That does not depend on the code block. It's constant across all the code blocks. Okay. Okay, so you take the code block, you put your CRC for the code block, which is 24 bits. And the remaining K minus this size, you put something called filler bits. Okay, filler bits are something that you just add. They are zeros. You just add them up. Okay, add them. So at the end of the day, this whole length becomes equal to 22Z if it is BG1 or 10Z if it is BG2. Okay, is this clear? Did you understand this part?
Correct.
Hello.
Those filler bits will become identity matrix in the LDPC, no, sir?
No. This filler bit, see, your LDPC operates on certain number of, LDPC has expansion factors, na? Yes. Based on the expansion factors, the number of input bits will be multiple of that expansion factors. Okay, I will show you one example. We just come to one example, then it will become a little bit clear. So your what do you say? Your LDPC cannot take arbitrary inputs, arbitrary number of bits as inputs. It has to have some fixed number of input bits. I mean, it will be multiples of some lifting sizes. Okay. But your code block, your transport blocks and code blocks need not be multiples of those. Okay. So what you do is you add a few number of filler bits. Okay. The number of filler bits you add will be generally less than the lifting factor. Okay. These filler bits are added for the encoding. After encoding, you will not transmit these filler bits. Okay, this will become clear in just bear with me for 5 minutes. This whole thing will become clear. Then we'll come back and look at this again. Okay, just keep this in mind, the filler bits, how we computed the filler bits. Okay, so what we did was, we found we have KB for each of these base graphs and depending upon the size. And then we find a lifting factor such that it's greater than the total number of bits you have. And then we said KR is equal to 22Z for BG1 and 10Z for BG2. Okay.
Here B dash is what, sir? K dash is equal to B dash by C. So B dash is what?
B dash was the total number of bits here. After
So
you do the
okay.
after you do the code block segmentation and add the the CRC 24-bit CRC for each code block.
Okay, sir.
That one's B plus C into number of code blocks into 24.
Okay, sir. B dash by C.
Okay.
Next slide.
Let's look at the next 3 slides and then we'll come back to this again once. Okay. Okay. I mean, all of you know this. I mean, based on the photograph defined by the parity check matrix, there are 2 base graphs and the code rates are 1/3 and 1/5. It will become clear in a minute why that is. Okay. Now let us see this thing. Okay, once we look at this, this will become clear. Okay, so there's something called the lifting set, lifting size. Lifting size is nothing but the expansion factor. Always remember, lifting size is nothing but the expansion factor. Okay, so we already chose the lifting factor Z based on this exercise. Good, based on the number of bits you have, and based on this particular whatever algorithm or whatever if conditions they give, you choose your lifting factor. You choose your lifting factor such that KB into the lifting factor is greater than K dash. Okay. So this is the lifting size set. So you have multiple lifting size sets. Okay. When you're choosing the lifting size, you'll also get an index called Z from 0 to 7. One index you'll get. Okay. So I'm just focusing on BG1 for now. Let's focus on BG1. So what you do is, if you look at the, I'll open the spec once. Let me just open the spec so that it becomes clear. Okay, so this is the base graph 1, base graph 1C. So base graph 1C, so essentially what they put here essentially correspond to the non-zero elements of your base matrix. Non-zero elements of your base matrix. Okay, so they give the row index and they give the column index. So these are the only non-zero elements of the base matrix. So what you do is you choose your ILS. So we have already chosen your ILS. Okay, once you choose your lifting factor, you also know the ILS. Okay, once you know the ILS, you choose that ILS. Okay, for example, ILS. So 0th row, 0th column, if you have an ILS of 4, it is 211. Okay. Similarly, if you have row index 1 and 7th column for 4th ILS, it is 76. Okay. So what you can do is, let's finish this slide and then I'll explain. Okay. So you can choose the correct column based on the ILS. Okay. And from there, you know all the non-zero elements of your base graph matrix. Yes. Now, how do you find your parity check matrix? Once you know the base graph matrix, this is exactly like what Andrew said. A little bit different. Andrew wrote -1 instead of 0. So here what happens, all the zero elements are replaced by zero size matrix of ZC cross ZC. ZC was nothing but the lifting factor. ZC is nothing but Z. Okay. So you replace it by Z cross Z matrix. Other elements, what happens is you got an element. Now you, for example, the fifth element, 0th row and 5th column element is 219. Okay. What you do is, you do the remainder with respect to Z of that number, and that will be your permutation dimension. Okay. What Andrew told was the base graph itself uses the permutation. Here there's a little bit difference. The base graph, in the whatever is there in the base graph, you just do modulo ZC, modulo the lifting factor, so that you get between 0 and the lifting factor -1, and then you do those many right shifts. Is this clear? So effectively at the end of your all this procedure, the base graph 1 will be having a size of 46Z into 68Z. Remember, base graph 1 was 46 into 68. Now if you expand this using the lifting factor size of Z, you get 46Z into 68Z. Similarly, 42Z into 52Z. Is this clear? Is this fine? Did you understand this part? Okay. So this is a parity check matrix. Okay. If I give you a parity check matrix, remember for a block code of length of dimension k comma n or n comma k input bits and output bits as n dash, the dimension of the parity check matrix is n minus k into n. Okay. So this is the dimension of the parity check matrix. So this BG1 will correspond to what code? It will correspond to 68Z, 22Z code. So you take 22Z elements and output 68Z. BG2 will correspond to 10Z elements input and 52Z elements output. Is this clear? Any questions here? I just stop here for 1 minute, look at it and ask me questions. Then we'll go back. Okay. You understand how I got the code rate, n comma k. Okay, based on the size of the dimension of the parity check matrix, which is given by this, I can compute n and k. Na? Okay, 46. So in this case, 68z is the n, and 68z minus 46. I mean 68z minus k is 46z. So k should be equal to 22z. Okay. So this, if you lift by a factor z, the code rate that the code input it expects 22z, and the output it will produce 68z. Okay, that is the reason why we chose in this case for BG1 we choose the input to be 22z. Okay, so the input number of bits should always be 22z, and you choose the z such that this 22z is always greater than k dash. K dash is the number of bits when you equally divide the bits between all the transport blocks, all the code blocks. Is this confusing?
Hello.
Hello.
Yeah, sir.
Dipanshu?
Said, yeah. Sir said 22z cannot be greater than 8448, or it can.
It will
Like
not be greater than 8448.
Okay. Sir.
Okay. So I put all of these things together again. So the output of code block segmentation is 22z bits. Just 1 minute. Okay. So sorry, this should not be 22 bits. So the output of code block segmentation, you get some bits. Okay. The input should be 22z bits. What you do, you fill, these are called the filler bits. These are exactly what I call the filler bits. The zeros, na? You put k minus k dash, 0 bits here. Okay, the input to the LDPC code is 22z bits. The
Output of CBS actually after transport block we get the code block. The code block size is fixed. So output of CBS means what?
I'll show you just. This is the output of with the up to the CRC point.
Okay.
Okay, then we fill the do the
Filler bits. Okay. Right.
Okay, so these 22z bits are fed into the LDPC code. Remember, the LDPC code is a 22z, 68z. So it takes 22z bits input and produces 68z bits output. So 68z bit output come. Out of this, what they do is the first 2z bits are dropped. The first 2z bits are dropped. This is called puncturing. This is the first set of puncturing where they drop the 2z bits. So effectively, you have 66z bits. Okay, the input is 22 bits. Effectively, after you do the puncturing, you get 66z bits.
Puncturing means physical meaning here. Puncturing is removing the bits.
Just removing the bits, puncture. You just remove drop the bits. Okay, the first C0 to C2Z minus 1 bits are dropped. Fine. So after this procedure, you get 66 bits. So effectively from the input to this point, the code rate is 1/3. The input is 22z bits. The output after puncturing is 66 bits. So effectively for BG1, the code rate is 1/3. So you do a similar exercise for BG2. Okay.
Data
They
will not
again
be
do-
useful data after puncturing.
Sorry.
That useful 2G we are dropping, sir. Any
Hello, Mr. Vijay, can you repeat it? Hello, am I audible?
He is asking what is the significance of puncturing of what I.
sir, is it audible, sir? No.
Yes, Vijay.
Because, yeah, yes, sir. Hello.
Vijay,
Hello?
continue. Tell me. Yes, I can
Yes,
hear you.
we are dropping 2G. We are dropping 2G bits, na, sir.
Yes.
So do we not lose the customer data, sir?
No, we won't, because the parity bits already has this information. Na? So you can recover this data using the parity bits. Okay. See, effectively, effective code rate is 1/3. What does 1/3 means? You have 22 Z bits, you got 66 Z bits. So you're replicating a lot of this bit information in some of these parity bits. So you can be able to recover those things.
Okay.
So I'm going to stop at this point. I want you to go through this set of slides again. Okay, because tomorrow I'm going to do rate matching, which is a little bit more, what do you say? If you understand all this part, rate matching is very straightforward. So please, I would suggest you, I'll upload this set of slides today in the classroom, okay, at least as a temporary basis. Please have a look at them, understand these parts once more. Okay, effectively, you think about what Andrew has taught us on the effective expansion factors and other things. Again, go through the slides, then all these things will start making sense to you once. Okay. Once we finish that, tomorrow in the next class, I'm going to tell you about rate matching. Okay, rate matching is a little bit more complicated. It's complicated because it's procedurally complicated, nothing technically complicated. Once we understand the rate matching, then we'll understand how do we change this code rate. Okay, so this is a fixed code rate at this point. Now but we have to change this to whatever code rate we want. We can change it to half, or 5/6, or any other code rate we can change. The way they change the code rate is, if you want higher code rate, you drop bits, you puncture. If you want lower code rate, you resend these bits again, these parity bits again and again. Okay, the exact procedure on how to do this is called the rate matching. Fine. So what I would suggest is, please take a look at the slides again up to this point. Understand all this, correlate with what Andrew has taught us. Okay. Once we do that, in the next class, I'm going to teach you rate matching and interleaving and other parts, and we can conclude this thing. Then we'll go to HARP. Fine.
Yes, sir. Thank you, sir.
Thank you, everyone.